Hi there, Hananiga AP Physics. I realized that I did not put any homework help up for gravitation number 3, so I thought I'd take a few seconds and just look over some of the problem pieces to it that we have, and I apologize if I'm a little wiggly here. I'm trying to hold my phone and do this, so I'm hoping that you can see this. Okay, number 4 I think is pretty easy. There's nothing you don't even have to use numbers for that. So that shouldn't be too hard to do, good old number 4. And you're going to use Newton's law of universal gravitation in order to do that, which for some reason in all of these, this is old. I keep calling this U. I don't want you to mistake that with potential energy. It's not. It's Fg. But I was calling it universal gravitation. So there you go. Anyway, let's take a look. Let's see. Number 6. Shoot, the way this is printed out, it's hard for me to read it. Okay, number 5, the one about the Cavendish balance. Let's take a look at that. The Cavendish balance, it says you are, measuring big G. You're looking for the gravitational force. That's a straightforward application. Watch out for the grams versus the kilograms. You want everything in kilograms, centimeters to meters. You definitely want that. Synchronous satellite question here. Now this is one like we did in class. Remember when we first got started on that? And luckily they've got a link to the table which has the values that you want for mass and so forth. Keep in mind what we're doing here is you are setting the satellite, the centripetal force equal to gravitation. Notice what's going on here. Here we're going to have the radius plus the height, the radius of the planet plus the height above the planet. That's the distance to the satellite over here. That will determine your centripetal force. R for this side is simply, it's going to be the distance to the center of the circle. So, perhaps that makes sense or not. Or I should say it matches really over here. And I think I forgot to square things over here. Whoops, let's put that squared in there. All right, do keep in mind that we are looking for, when you're taking care of this, we want a linear velocity, right? So we want the circumference of our circle, 2 pi r, right? 2 pi r over the period to find our velocity. Let's not forget that. All right, if we just did 2 pi, that would be an angular speed, but we want the linear speed. So 2 pi times the radius, and that will, and our radius, of course, is going to be the height above plus to the center of the planet. So a little plug and chug there. Let's substitute it out for this v squared. Space probe fired as a projectile, and we are looking to find the speed very far away from the Earth. It may surprise you to think that there is speed, but remember, when you get far away in terms of energy, what's going to go to zero is your potential energy, not necessarily your kinetic energy. So you have to have initial kinetic energy to get away, plus the gravitational potential energy based on being on the surface of the Earth. That's going to be equal to your final kinetic energy. And you're going to then, solve for this V over here. So watch your math, be careful. Okay, last question here. You're looking at, and they give you a picture. I have the picture on the other page, as a matter of fact. So you are looking for the, sorry, I'm trying to read and hold this steady and look back and forth, so I'm making a mess of it. We want to find the escape velocity on the far side of the planet. Okay, so this one's a little different. Let me put this on in here. Okay, the distances they're giving you are a little bit different than maybe what you are used to. All right, so here's this object. It's on the far side of the planet. So the radius of this, of this moon, you're going to have to do when you figure out your potential energy. Right, if you take a look over here, we're going to infinity because that will go to zero, obviously. But we have potential energy with respect to the larger planet. We have potential energy with respect to the moon, and then you've got the kinetic energy that it's going to need to go anywhere at all. But key thing that you need to keep in mind here is that this one is obviously going to go to zero. This one, this r is not, technically it's not r, it's this distance plus 2r, which is for the moon itself, not the same value of r, obviously, but you have some addition to do here to get this value underneath. All right, he's going to do the planet all the way to the rocket, so watch out for that. For the second UG, this one, you're just going to need the radius of the satellite. That has to do with the satellite up to where, or the moon's radius up to where the satellite is. Said that wrong. Okay, so no addition required there. That's why when I looked over here, all I have is that distance, that radius of the moon itself. Okay, and ultimately we're going to solve for that v squared. So again, lots of numbers, lots of big numbers. Go slowly and carefully and calculate. All right, hopefully this one didn't require too much time getting help, but hopefully you have help where you need it. Come see me if you've got questions. We do have a late start tomorrow though, so I should be available pretty much right at the beginning of that. Okay guys, talk to you later.